Good afternoon, everyone. Thanks for coming to our seminar and for Camille for a great introduction. We're going to be presenting our work from the spring semester, or 653, in which we developed a low-cost modular autonomous water sampler for coastal biogeochemical monitoring. So this is our team. I'll start by introducing myself. My name is Cameron. I'm an oceanography student, and my research project focuses on carbonate chemistry, and my interests extend past that into geoengineering and ocean instrumentation just in general. I worked on the software and a little bit with the circuitry.
Hi, my name is Kara Reinhardt. I'm a master's student in ocean resource engineering, and my research interest is in ocean instrumentation, and I mainly worked on the sampling unit.
Hi everyone, my name is Darren. I'm also a master's student in ocean resource engineering. My main interest is in wave energy conversion, and I worked on the electronics portion of this.
Hi, my name is Olivia DeCroix. I'm an ocean resources and engineering master's student. My research is in biomimetic marine robotics, and I primarily worked on the manufacturing of the housing.
Hi, I'm Maria. I'm a master's student at the Ocean Resources Engineering Department, and my research project will focus on flow feature reconstruction based on pressure distribution on nearby bodies.
So this is a brief outline for you guys, what we're going to be talking about today. We're going to first start with the project scope. We're going to give you an outline about the rationale for our auto sampler, as well as the relevance and greater auto sampling. We're going to go over our housing, in which we go over the manufacturing process, price breakdown. We're going to do the same for our brain sampling units. I'm going to show you our final product. We're going to discuss some future modifications, and then we're going to give you that demonstration. So I think it's first important to explain why we even collect water samples. So in the ocean, we're constantly trying to resolve biogeochemical processes, namely ocean acidification right now, nutrient dynamics, and also we're trying to characterize water masses, as well as resolve not just temporal dynamics, but also spatial dynamics. Currently, we're collecting water samples. These are human-powered efforts. They're grab samples, and they're limited in their temporal and spatial resolution. So we have a couple of examples here, and the sampling capability is really just limited to going out and collecting the sample yourself. A more expensive alternative for oceanographers and ocean engineers is to go on a ship and collect water samples, and this is kind of one of the most prevalent sampling techniques, using a CT rosette and a Niskin bottle sampler. So again, these are limited in their spatial and temporal resolutions because you're taking discrete samples at specified depths or conditions. And not only is it expensive to deploy the rosette on its own, but you also need to pay for people's salaries and also like the cost of the actual ship time itself. This also, with the advent of modern technology, we've seen more work on collecting water samples autonomously through auto samplers. And these, conversely to these traditional techniques, have a much higher spatial and temporal resolution. They can be costly in terms of not just their price, but also the manufacturing process, and this can also hinder their availability to consumers. So these auto samplers can be inaccessible, and by that we kind of mean, they have custom fabricated parts. They require specific skills or machining, and these are purpose-built. So we have a couple of examples here, and these are all coastal kind of auto samplers, but they're purpose-built, and so oftentimes people find them hard to adapt to their specific needs. Our project is situated within a larger effort to understand a coastal urban fire in the 2023 Lahaina wildfire project. So these are some of our awesome collaborators, a couple of grad students in oceanography and a lot of PIs. And in the next slide, we can see our actual PIs. And so this project was designed to characterize the coastal biogeochemistry in Lahaina, and doing so in different metrics. So we have Andrea Kealoha working to understand reef metabolism through carbonate chemistry. And we have Nick Hako, who's trying to understand the trace metals and how they affect reefs as well. And then we have Craig Nelson, who's trying to come at it from a biological angle with microbes and organic compounds. And then Eileen trying to understand the environmental contaminants and risk assessment. And then Camille, who's coming at it from the engineering angle, and how can we sample all of these things and understand these processes. We were presented to us through a couple of meetings with the PIs, the following design criteria. So they had a couple of musts, and that was the autonomous discrete sampling, like a simple user interface for people to interface with the sampler, multiple programmable channels, the ability for the sampler to collect 1 liter samples for 36-hour periods, and for the sampler to be easy to assemble and operate with no technical background. They also identified that they'd like to have some wants and not needs, and that being the in-situ filtration and also the sampler being trace metal clean. So with Nick, he's interested in trace metals, and often metals used in some of the auto sampling parts that we used had trace metal sensitive metals.
After defining our requirements, we then conducted a literature review, and we reviewed 51 different papers, and we found out that majority of them had some key issues that were limiting their usability. First one, they were expensive. Another was that they were not replicable or open source, or using open source software that we could find. Another one is that they're not customizable, again, meaning we can't put in a new sensor to try and sense something new without having to redesign the entire system. And then lastly, they're generally difficult to deploy, requiring ship time, or difficult for one person to deploy underwater by themselves. Our proposed solution, the modular autonomous water sampler, is built to address the current limitations in water sampling methods. So we designed it to be modular, meaning that one can just add more sampling units and subtract them as they need to. It'll be accessible, meaning that anyone could build it, anyone can use what we've made, a build guide, our code to add on what they want. And then it'll be affordable, meaning that it's made of off-the-shelf parts. Next, we're moving on to the housing. In the housing, I'll go over our inspirations, the components, and then the cost analysis. Our inspiration was the Blue Robotics water samplers. However, these are generally expensive, and so we designed it using PVC tubing. We cut at 18 inches, and then a sled, which we made out of PVC sheets, and then 2 acrylic discs where we drilled holes and attached 2 L brackets, and then added Velcro in order to make sure our electronics attachments are secure. Next, in order to ensure that our wiring would not flood our housing, we then used 4-inch acrylic discs and drilled more holes into them to attach penetrators. And then in order to seal it even more, we had an end cap where we again added penetrators, and then our union in order to ensure easy access. The manufacturing, with the main goal of being easy to do, was done with hand tools, even if some tools could be replaced with industrial machinery. They were first tested with hand tools in order to ensure that they were easy to do. Our sled was primarily cut using a bandsaw, however, that could be replaced with a hand saw. And then the penetrators holes were created using a hand drill and tap set. Some manufacturing challenges was that in order to attach our pump, we had to use a pre-existing pump, which had generally weird spacing and odd hole sizes. which caused some issues with finding the correct tool to do that. Another one was the physical limitations of hand tools, and they were generally time-consuming to create. Our cost was generally about $270 for the housing alone.
So I'm going to go into the brain of our system. So the two main components that go into our electronics was our Arduino Uno R5, which is a Wi-Fi connected interface for remote programming. That ran us about $28. And then we had a Cobalt 24-volt lithium-ion battery, which is small and easily accessible. You can get at Lowe's or any other hardware store that you're looking for. And that was about $49.98. So going back to what Olivia was talking about with our sled, all the internal electronics are mounted on that sled through Velcro. Each of our individual components are shown here. I'm going to go into those a little further in a more clear picture, but this is what the inside for our sled area looks like. So going to our circuitry, this is the main circuit here where our red lines are our power, our black lines are our ground, and the blue line is our data or the command from the Arduino that runs to our motor. So we're going to go bit by bit. So first, starting out, everything comes from our 24-volt battery pack. So that's 24 volts go into a 30-amp fuse, which allows us to protect our circuit in case anything happens, because we're working with live power. So that's also why we have that on-off switch. So when you're plugging it in, you're not dealing with that live power, but when you are, we have that fuse to protect the rest of our circuit. And then we go into our terminal block, which allows us to safely split our voltage lines so that way we can run it to our Arduino and to our motor separately. So from that terminal block in the middle here, we're seeing that we're going to our LM2596 buck converter, which drops our voltage safely from 24 volts to 5 volts. That is what our operating conditions for the Arduino Uno is. So from the Arduino, we then go with that 5 volts into our DC 5 volt relay module, which operates as our electronic switch or trigger, where our Arduino command will basically tell it to say, this is when we want it to switch on the motor, this is when we want the motor switched off, and that is what allows that to happen. And then everything else connects to our Topsun 120 watt DC to DC converter. So the reason we're using this buck converter instead of the one we used previously is we tested it with the other one, but the requirement for this pump is a 0.3 amp current and 12 volts. We were getting 12 volts with the other buck converter, but our amperage was in the milliamps range, so it wasn't enough for our pump to run how we needed it to. And then obviously we have our pump, which Kyle will go into more later. Yeah. So all in all, our cost analysis for our electronics ended up running us about $170.
Getting into the sampling unit. The sampling unit consists of a couple of major components like our pump, our sampling bag, and some minor components like zip ties and warp connections. Some of these components were provided to us by our collaborators, and some of these components were picked by us through a vigorous process that we get into next. So the first thing that we were trying to figure out is which pump do we want to use. There is many different pumps, submersible pumps, non-submersible pumps, different flow rates, different power requirements, different costs. These were the main 5 pumps that we're kind of looking into, and the first one that we ordered and tested out was the German Wonder Pump. So the German Wonder Pump is a submersible pump that is a 10 liter per minute water pump that is a really high flow rate. It only cost $55, and we put it in a tank and it worked. So we were very excited, yay, we got a submersible pump, don't need to worry about waterproofing. However, we realized very soon there is a contamination hazard. We have the water going through the pump, we don't know what's in there, and we cannot clean it out. So we decided to not continue with the German Wonder Pump, but instead focus on peristaltic pumps. And those were the 4 that we were left with, and well, with others, but these were the ones that we narrowed down. And some of them were too expensive to us, some of them were too low flow rate, and others were inaccessible or only available on very certain websites that are not accessible from every single country or for every single person. So we found the winner, and the winner was the Kamer KPHM 900. This is a 900 milliliters per minute peristaltic pump You can find it on Amazon for $89 plus shipping and tax. It has a 12-volt DC brush motor and is easily assemblable and disassemblable, which is very important for us because we were considering and ended up switching out the tubing. In our test, we had the pump run at 875 milliliters, sorry. So this was something to consider when we wanted to fill up the sampling back, but we get into that in a little bit.
In order to create a housing for our pump, even to make sure that it was submersible, we used another union and some more 4-inch acrylic discs. These were then, once again, added a penetrator to it and then attached using our waterproofing that we will get into later. And then in order to attach the pump, this was the part that was generally more tricky than others, was because this is where we needed to take the metal plate off of the peristaltic pump that we ordered and put it on the acrylic disc and then line up the holes and attach it. And so, as you see here, we were generally successful with this.
So next we go into our tubing. As mentioned before, we had a contamination concern. And so for our tubing, we're kind of wondering, is it replaceable? We figured that out. Yes, we can replace it. We get into that. How does it impact the flow rate? And also, contamination hazards. So we reached out to our collaborators and asked them if they had used specific tubing before, if they prefer some type of tubing, is there some standard that they apply to? And in the meantime, we figured out what the tubing size was that was in the pump already. And we ordered some tubing of that size to kind of work with that for the meantime. So we did that, and to replace the tubing, you have to completely open up the pump housing, and then you can replace the tubing, but you gotta make sure you grease it well, and then place it, and then you gotta, that's something we figure out, run the pump, which is basically you soften up the tubing so it runs better, because before that we had issues where we were kind of not freaking out, but getting a little, nervous because the tubing was not working. But with all these steps, it worked. But once our tubing came in that our collaborators provided to us, or gave us the specifics for, we learned that it runs without any adjustments. So this was platinum pure tubing that some of our collaborators preferred. However, the trace metal PI, he would obviously prefer without platinum tubing, but we know now how to replace that. So getting into our sampling bag, these were provided by us, to us by our collaborators. These are Tedler bags, 1 liter. The only issue we had with these bags in our process was that the inlet was really small. You can see it up here. So we had to find a way to connect our big pump tubing to the small inlet. So the connections, we just found a simple solution. It worked. We used plastic barbs to connect all of them and a bunch of zip ties. And it helped pretty well. Coming to our filtration, so one of the secondary requirements, design requirements, was that our PIs wanted in situ filtration. So the ones that they wanted is the 0.4 micrometers PC membrane. So we tried to make this work first before we looked at any alternatives, and we got a big problem there. So whenever we put the filter in, the tubing would fly off because it created too much resistance. So we tried to adjust it by adjusting the filter holders. We were threading them to kind of twist the tubing on. This was somewhat working, but at some point we just didn't have a flow rate anymore. It was just like backing up into the pump. So we found this filter holder, the Advantic 47 millimeter filter holder, and with some adjustments by cutting off a tiny piece on the back and then placing a longer plastic barb on it, we were able to fit the tubing on there and secure it well with our zip ties. And this worked really well. Yes, so this is our final setup. We have the pump on the left side with the new replaced tubing going into the filter holder and then connected with the zip ties and the barbs into our little connection to make the tubing a little smaller and then into the sampling bag. So we started testing our setup, and with a 0.4 micrometer filter, we did have a very, very low flow rate. It was dripping, but it's definitely not ideal. So we tested out some other filters, and these were working a lot better. So no filter gave us a 1 liter sample in 63 seconds. 1 micrometer glass filter that you can see in this video placed in the filter holder gave us a 1 liter sample in 64 seconds. And we even tested out a 0.2 micrometer inline filter that has a different material than the filter in the previous slide. It gave us a 1 liter sample in 66 seconds. So the total cost for the sampling unit comes out to around $225. If you consider the housing on top of that, then every additional sampling unit to the modular auto sampler would be another $250.
All right, now getting into our software. So the entire MAWS unit is powered by the brain, and it's an RTC code. It's pretty interesting because it allows the user to remotely connect to the entire sampler through a Wi-Fi network that the host itself. So in doing that, you can actually control the and this is pretty significant because doing field sampling on a boat or somewhere with a service, you don't really have to connect to the pump physically or by it hosting its own network, which I tried first. Also, I tried to use native functions in Arduino. So, regardless of version history, you should be okay. It uses one package, which also is in the Arduino library, and I did look that it's compatible regardless of whatever version you're using. As per our collaborators, I tried to design it so it's a really simple user interface. It's less than 150 lines of code, and it takes, I checked earlier today, it takes less than 2 seconds to flash or upload the code onto the Arduino. And there's only 2 commands. So you can either specify the start delay or the runtime. Both of them have like a default that will just run if you click run. So the start delay in milliseconds is how long from now you want the pump to start firing. And then the runtime is how long you want the pump to run. And so here's a schematic that shows how the software works. So this is still an Arduino when you have to connect the board physically to your computer. You flash or upload the code, and then it'll tell you the name of the network, what to connect to, then to upload. This is just like your local IP address. It'll be different for everybody. And then you can close the whole auto sampler up. And then assuming that it has power, it'll always be generating a network. And then so you can just see in step 3 here that just like any other network, you can just connect to it, the pump controller, and then once you're connected to it, it's password protected, and then you would be able to join it by visiting the IP address that's specified in your Arduino code, and then you have those 2 user commands.
Finally, it's time for fun topic, waterproofing. Actually, waterproofing is very important because if we have leakage from anywhere, it can cause damage to the brain and motor and stop working. So it's really important to waterproof the whole system because it's supposed to be submerged, the device submerged at the depth of 10 meters. For this purpose, we use a variety of material, self-fusing silicone tape. This one, it is a kind of sticky that can stick to itself, and it's very stretchy and it's very easy to work with. And electrical tape that we can use this one for waterproofing wire. Plumber's putty, it's a kind of moldable and removable putty that you can apply for anywhere and anytime that you want, you can remove it easily. Epoxy glue, it's obviously glue that you can use to stick anything together, and epoxy. Epoxy putty is a kind of dough that at first it's very soft and flexible, but after some minutes, it can turn to a hard rock, and you cannot remove it at all. But to figure out which material works better and with which one you can get desired result, we did a bunch of experiments. For the first step, we covered all the gaps on the pump housing with the tapes and using epoxy glue for fixing the plate to the union. We put into the water and we quickly fed. There was leakage. And for the second atom, we replaced the tapes with the plumbing, the removable. But at this time, we sealed all gaps on the pump housing, and in addition to this, we sealed the connection between the pump housing and the plate, and again put it into the water. We had still leakage. But at this time, we made a new decision. We thought that if we could block water from reaching the motor, it wouldn't matter anymore if we have water into pump housing or not. So at the next step, we tried to sealing motor. We open this plate and motor. We put epoxy glue around the motor and fix it. Again, we have leakage from around the motor. So we figured out that we cannot seal perfectly the motor. What was the decision? We just figured out that we can seal the pump housing completely. So by this decision, actually, we sacrificed some part of our modularity, which is one of our goals. Because when we still completed the pump housing with permanently, we cannot open the pump housing for further action, for example, changing the tube or any other possible problem. But we didn't have any other choice, so just to save time, we sealed two pumps. One of them was sealed with the epoxy glue, and one of the other one was sealed with the hard putty. Again, put it into the water, and again we had leakage. But at this time, we figured out that we had leakage. We have water inside of the union, but we didn't have water inside of the pump housing. So we should find that where is this leakage. Here in this video, you can see clearly the air bubbles that came from here, the epoxy glue that was between the plate and union. And in this picture, you can see the water inside of the union. Up here, you can see. So here we know that we have leakage from the epoxy glue, but we weren't sure that if we have leakage from penetrator or not. So we decided to seal all around the plate with the hard putty to see and to check that if we have leakage from anywhere else or not. And finally, we seal everywhere with the hard putty, the connection between the plates and union, and all around the pump, and all connections with the hard putty, and put it into the water. And finally, yeah, we did it, and there were no leakage, there were no water inside of the union. So after getting this result, we put it all packaged into the water for 24 hours, and after 24 hours, we didn't have any water inside of the union. But one interesting, when I wanted to apply the putty here, at first I forgot to put the ring on, And I just simply keep this one and apply the putty around this and let it dry. And after that, when I wanted to put the ring on, I saw that I cannot, because the putty, here was very thick and it didn't let the ring on. So I had to sand all around this one to make it thinner to let it ring on. So it was actually a problem that I was faced, and I wanted to mention this. But anyway, yeah, after applying the hard putty, we could waterproof the whole system perfectly. And here you can see the total cost of waterproofing material, and it is around 120. Okay, it's true that we had to sacrifice some part of our modularity, but at least we could keep the cost at a reasonable amount.
So coming to our final product, now that we have the waterproofing done, we were able to put the sled into our housing and close it up with a union, which allows us to open and close it whenever we want to. And yeah, you can see a video here of the lady placing the sled in. And we ran some final tests to make sure that the waterproofing is in fact working, and we submerged all water sampler. We placed a 1 microliter glass microfiber filter in the filter holder, and we ran it 2 times. And the first time we ran it for 69 seconds and got a 950 milliliter sample. Second one was 850 milliliters for 60 seconds, which gives us 1 liter, so a whole sample in about 72 seconds.
So our final cost was about $780, which, while a little bit more than what we would have liked, we were still very proud of the fact that we were able to accomplish this. So the general tools we required, the housing required quite a few, including drill sets, 2 different types, one being a step drill and then a regular set, a tack set, screwdrivers, bar clamps, a hand drill, a deburrer, files, and tap oil. The electronics required a voltmeter, soldering kit, wire strippers, funnel crimpers, and a mini screwdriver. Our sampling required wire cutters only, and then waterproofing only required rubbing alcohol.
Okay, getting into our future modifications and where we're trying to take this next. So while we're pretty happy with what we did identify a couple of things that we wanted to improve upon in the future. Firstly being the additional sampling capabilities. So we did have a 1-channel relay, which basically means we could only dispense 1 sample per the brain. And so I'm sure you saw earlier that we have like 8 penetrator caps, which means we can have 8 different samples. And so we just have to increase the relay board to have more channels, which is a pretty easy plug and play. And then also, as Kaya said, we'd like to make this a trace metal clean sampler because one of our collaborators did identify that this was crucial for their research. We also thought that it would be important and would improve the accessibility for people to have that onboard data storage. And so it would basically provide the user like sample collection time when it was collected, and then it would perform some computation so you can see from how long the pump was firing based on that, how much volume you actually were dispensed, since the amount of water is crucial when you're doing lab analysis. And then also we're hoping to do some field tests and compare our auto sampler to traditional water sampling methods, that being the Niskin sampler here on the left, and just like a normal grab sample, and just see if our solution is viable. Just a few more modifications. We also, as Kaya said, we had some difficulty trying to generate different filter options. Because sometimes when we're collecting organics, you want to make sure we're flushing out all those little microbes. Yeah, so we're going to look at that in the future. And then also, we didn't actually end up having time for it, but this study is going to be performed, or the auto sampler is going to hopefully be used in like a coastal area, so in a reef, something like 20 meters, and just make sure it's actually rated for what it is, because it's just a PVC housing, and we want to make sure it's not going to detonate, underwater. So, and then lastly, so another software thing, pretty simple fix is just to make some graphical user interface, like an application for people where like you're given a clock and you say, when do you want the sample to be collected, how long, or like what volume do you want, and then they don't need to count milliseconds. You'll see on the example, but you have to do some mental math to calculate how long you want your sample to be collected for. Lastly, we'd like to acknowledge all these great people who helped us during the building stage, the thinking stage, and keeping our hands and fingers and not burning the lab down. So that was great. And then also we want to acknowledge our funding partners, the Manoa's Strategic Investment Initiative and the SOAS Dean's Office. So thank you. We're going to be taking some questions after our demonstration, but you can see kind of the chaos that ensued over the past couple of months. So yeah, thank you guys. So Camille, I also realized that if I connect to the network on my computer, the Zoom will crash because it doesn't. So maybe, should I host or should I connect on a?
I can say you want
to connect on your phone?
I can get my computer.
Okay.
Yeah.
I guess you guys won't be able to see, but this is pretty much what it will look like.
What, online?
Yeah. Yeah. So we're literally just going to be doing this. Anybody could connect, but don't. Yeah. Password connected.
We also found out that it overrides the Wi-Fi, and so we tried to present one time, and we couldn't because we were on our sampler's Wi-Fi instead. Oh no.
All right.
Okay, we got our auto sample right here with the brain right here, and then this is the sampling unit with the filter and the sampling bag. No, not yet.
Can I see you?
Huh? I can move around. So thank you, Mike, for all the equipment that we stole from the lab. We're using a dive float to submerge it right now because the brain is buoyant and will float on the surface otherwise. And then, submerge everything. Very important step is to open the valve in the sampling bag, otherwise it will just fly off. Okay, as you can see, everything's submerged in the water now.
Okay, so I'm basically going to tell it, as you can see on the slide deck, I kind of have to just say how long I want the pump to fire for. And like I said, we calculated that if it fires for 71 seconds, it'll collect a liter. So here we go.
See where the sample bag is pulling out.
So think about all the stuff you could be doing now. You don't have to collect the sample yourself. You know? Yeah. many samples did we say you can collect before the battery dies?
66. If it's at full charge, which currently isn't because we've been testing it all the last couple months.
So maybe 66.
Stop it, stop it, stop it, stop, stop. I don't know.
It's gonna explode the bag.
Okay, not sure why that continued to go. You got it? Okay.
It's disconnected every time.
It has to, you know. It's a show effect.
Have to be extra today.
Yep. Okay, this is our first sample. You still see a nice full bag. You can give it
Yeah,
around
that
if you
was-
would like to.
That was user error. I clicked the button twice. Yeah, that's my bad.
Maybe I wants to, I don't know, seven that way. That's a water sample, 1 liter.
Just set it there.
Okay, well, we gotta show another one for redemption.
We're gonna do a
So,
redemption.
where's the, okay,
Here, wait, no, I think we're gonna do it into the beaker.
you want to
Do it straight into the beaker.
the second sample?
Yeah.
Okay. I'm going to show you that it's actually 1 liter, straight into the beaker.
Once it stops.
Sorry, just stop.
But it's working. Okay,
Okay. Yeah, I'm
I'm gonna
gonna
bring it over here,
We'll just wait for them to get it. Do I need to hold this?
maybe.
Okay.
That works.
Okay, ready?
Ready?
Yes.
Just can't say that.
I guess another thing worth mentioning is that one of the ideas that we had that like having the brain separate from the actual sampling unit is that if you had multiple samples, you would organize it like a rosette. So that's like you'd have like, traditionally you have like a CTD in the middle and then different Niskin bottles. And then you could have this a similar way.
Yeah.
Okay. There
It's the show effect.
we go. Apparently.
Okay, so say I clicked it once and it fired on. Yeah.
We got redemption.
Yeah.
This is what it looks like, and this is if that it works.
Okay.
Alright.
Any questions?
We have a Zoom question first, maybe we'll start with that.
Take it out.
Okay, we got a question from the DLNR in Maui. Very cool project. Solves a lot of problems we regularly encounter in the field. Oh, it's just a excited to see where this goes. Thanks, Toba. Okay, and then we got a question from Nick. He says, very cool, everyone. How long do you estimate it would take a new user to make one of these?
Hopefully with the build guide, probably month in general, I would hope. But we haven't timed how long it would take to make one without all of the trial and error we did.
Yeah, and one of the, at least in the grant that Camila and the other Latina PIs, they wrote this class into is that a class of undergrad should be able to build them. And so I think that if we had, like a semester long class, you could probably, with the build guide and the kit and the coding, you could definitely make a few of them, so. We have one more Zoom question. You tried several filters of different porosity. Did you have a design requirement for a particular diameter cutoff? Example, a filter at 100 microns and larger.
So yes, I reached out to our collaborators and they expressed that they would ideally want the 0.4 micrometer EC membrane filter, which is the one that we showed in the first video, which ended up having a very, very low flow rate. So that would be like ideally the design criteria. Different materials will filter differently and give us different filter rates, so that's something to test out in the future.
Hopefully you can hear that.
So it seems like the filter, causes a lot of complications. Is there a specific reason that you need to filter the water at the time of sampling rather than at the time of analysis? Like you're not performing the analysis on board, right? You're bringing it back to a lab.
Yes, so from my understanding, our collaborators mentioned that if we have the water sampler deployed, it will stay there for a couple of days, and they would ideally want as many organisms out of the water sample as possible to avoid any further contamination or biofouling in the samples.
I was wondering about the dead volume on the tubing, and if there is a way to flush the system before you take the sample into the bag.
Yes, so our current setup has water in the filter first, which is obviously not ideal. So the future modification would be to either flush it, as you mentioned it, that would be possible if you place the sampling back on after, or place a solution that will not impact your sampling, the water sample, in the filter bag and in the tubing before deploying the water sampler.
But at the moment, that's not the case.
At the moment, that's not the case.
But like maybe for your case, you could put like an alkalinity blank or something in there, and then it would flush it out, and then.
For any chemical analysis, you may need to flush that because if you're going to take a sample 1 hour, then you're going to take another sample another hour.
Yeah.
You want to see, you don't want a contamination with whatever was in the tubing sitting for an hour.
Okay.
Yeah.
Yeah, we have another question. Did you have a pressure depth design requirement?
Generally, they asked for at least 10 meters, but preferably about 20 or 30.
So like, yeah, reef. We were trying to design for a reef, yeah.
Any other questions? Agreed.
So is there a specific reason other than availability that you guys were using zip ties rather than hose clamps?
Rather than hose.
So like zip ties, you can only tighten as far as your hand can hold them. Like hose clamps are designed for that purpose.
Right.
Was it just because zip ties were available, or?
Zip ties were available in the lab and they worked. They were never the point of failure. So.
I was gonna say that, yeah.
But that's on the outside of your tube.
Yes, but they don't want any metal anywhere near the sampling and trace metals chemistry.
Okay.
Yeah, like the trace metal contamination is on the order of what, nanograms? Yeah, so like if they're measuring those in situ and you have any kind of, yeah, it's contamination risk.
So I'm still not convinced it would actually get through the tubing, but yeah. I just in the future, like when you have the overpressure blowing your hose off of the barbed fitting, like a hose clamp would prevent that.
Gotcha. I think it's not so much about going through the tubing, but the water in contact around the water sample would be in contact with the plant.
So wouldn't it react more, foul more, like the ties of pretty standard, they don't mess up easily, and if they're gonna put it out for a month.
I mean, we can talk about it. Yeah, I mean, the hose clamps you can.
I love zip ties.
You can also easily remove those. I'm not familiar with those clamps.
Maybe a dumber question, just because maybe I missed that part. But So you have like one sample bag attached, and say you want to take a new sample, are you gonna drain it and then, like,
So-
or are you gonna have multiple bags?
To get the multiple samples, the way our sampler is set up, that is, you would add another sampling unit to it.
So would that be like human powered?
You would add another whole of this setup to one of these boards here.
And then you
Oh,
can
okay.
take up to 8 different samples, and then you would have to retrieve it and
So it's
replace
like
the
a
sample.
CT, like.
Yeah,
Okay.
like a rosette, yeah.
So, yeah, you would eventually have to take the sampling back off, but only when you retrieve it. If you want more samples, you can add sampling units.
Kendall?
What's the max range of the Wi-Fi in case you guys like throw it off both?
Well, we were initially skeptical that you could even connect to it like when it's submerged in inches of water, and it worked. We haven't tested it in salt water, which could be more complicated. There's a lot more like electrical connectivity that might interfere with it, but honestly, I don't know. So, yeah.
The way this is set up though, is that if you deploy it, you would set up the delay, or
Yeah.
in another case, the starting time before you even put it in the water and hit the run. So if you say, okay, it's supposed to sample at 1 o'clock, then you can deploy it at 12, set that before you deploy it, and then it will automatically do that once it's underwater. So there's no need for connection while it's in the water.
So I guess you just have to remember where you put it.
Yeah.
I remember where you put it, that would be ideal.
Yeah.
That'd be good.
Cool.
Any other questions?
Leon?
What did you learn by doing this?
A lot. Don't underestimate hand tools. Those were some of the most challenging things that I had to work with.
Building something is a group effort.
Yeah.
I feel like it's, yeah, definitely looking at everyone's section. Couldn't have done that, just one person, I think us working together made it happen. So.
You also need a lot more people to it than just the 5 of us here. Like there's Jim from just next door who helped us out, gave us some ideas of what to do. I met up with a couple people, a couple graduate students from oceanography who like just walked me through their lab and showed me a couple filter options that I wasn't even aware of. So it's
I received help from the ME department in their use of their shop in order to help manufacture stuff. So yeah, definitely a collaborative effort, not just between the 5 of us.
Thank you very much.
Thank you.
Thanks.